So today, me and Mehdi will talk about training on AMD GPUs. So if I can. No, I've moved too far. All right, so just a quick overview on what we'll talk about. We'll give a brief overview of what AMD hardware is, the GPUs, some of the capabilities. And then I'll talk a little bit about the ROCm stack, the software that actually runs on these GPUs. And then we'll talk about training. Training, as some of you may know, is a very broad field. It's very difficult to categorize into, there's thousands of different ways to train, but at a very high level, we'll try to capture it into three main categories. Pre-training, which is where you train really large foundation models like the Meta Llama or the OpenAI models. When they train it from scratch, they use thousands of GPUs to train these foundation models. That's called pre-training. Once you have these pre-trained models, you can fine-tune these models. This is basically when you have some data set and you're trying to target your model to specific use cases. How do you fine-tune it rather than going through the full pre-training? And Mehdi will talk about some novel innovative things we've done with post-training. Post-training is sort of a middle ground between pre-training and fine-tuning, where you can actually change the architecture of the model and try to improve the performance of the model, either by accuracy improvements or inference improvements, and he'll talk a little more about that. And at the end, we'll leave you with some public documentation. How do you get started on AMD GPUs? I know a lot of you may be familiar with how to get started on NVIDIA GPUs are more prominent with that, but getting training going on AMD is equally easy, if not easier, and we'll show some documents on that. Great, so I'll start with what is AMD MI300, one of the GPUs that we launched last year. These are really powerful devices. Like an MI300 has about 153 billion transistors in it. It has 192 GB of HBM RAM. And compared to the equivalent NVIDIA part, for example, they have 80 gigabytes of HBM. So it's equally capable with additional memory capacity. It also has a lot of bandwidth to interconnect across different GPUs. And these devices, for example, if you're trying to inference a 70 billion model, you can easily fit this into one GPU. So it's really, really capable devices. And what makes it even more interesting or unique is because you have good connectivity across GPUs, we can get 8 of these GPUs together in a single node or a server. And essentially, these can now work as single giant GPU because you have really low latency connectivity across all these GPUs. And with the combined memory capacity of all of these, for example, Meta Llama 405B, Meta exclusively runs 405B inferencing on these devices because you can fit all of it in a single 8 GPU pod, and you don't need to go across multiple servers to account for the overhead from communication, things like that. So that's the MI300, which was launched about 18 months ago. AMD is continuing to launch newer devices as we go along. MI325 was launched late last year. And just on Thursday, we had a launch event where we launched MI355. And if you see the performance curve, it's starting to accelerate very, very quickly. And with MI355, it's not just about adding more compute, more power, but there's also lots of innovations in data types. Like we have microscaling, FP6, lower precision data types, which also account for good dynamic range. So you get good accuracy. At the same time, you're getting really high performance. And as we move forward, MI400, this MI500 being planned, at a yearly cadence, we'll launch new devices, and the pace of performance keeps accelerating. So next, I'll talk a little bit about software. Once you have hardware, to really make the best use of it, you need to have good software capabilities. So if you look at the stack, at the bottom, you'll see the AMD Instinct GPUs. And at the top, you see PyTorch, which is like the framework maybe a lot of you are familiar with, an abstraction where you can write code and train. Intermediate, there are a few software layers which actually you need to get really good performance on these devices. So the layer just above the hardware, you have the data center infrastructure or cloud that cloud providers like AWS or OCI, Oracle provide. This is just monitoring the clusters. How do you get access to the nodes, things like that. And I think earlier someone talked about containers. That's the layer above where you package a whole bunch of libraries that are required for your inferencing or training workloads. And then you can move from one GPU to another and expect consistent performance. So it removes all the contention of different libraries, things like that. And on top of that, we have ROCm, which is, if you're familiar with CUDA for NVIDIA, ROCm is the AMD version of CUDA. The big difference being it is open source. So we contribute a lot to ROCm to make sure you get the best of AMD devices. But because it's open source, the community can also contribute back. And hopefully that creates a flywheel of innovations or improvements that accelerate the pace there. And using these, we have training Dockers that we release at a bi-weekly cadence, which get really good performance on these devices. So there are lots of tutorials, but if you go through it, it's just a handful of line of code for you to get started on AMD devices. And I'll talk about it a little bit at the end of the talk as well. So with that background of what AMD hardware is and the software that enables these capabilities on the hardware, we'll jump into some of the training aspects. I'll start with pre-training. As I talked about, pre-training is about how do you scale your training on large number of GPUs. But before you jump into that large cluster, you want to make sure that you get a really good performance on a single GPU or single node first. So that's where we start. When we start training these models, we want to make sure that you get really good performance on a single node or single set of GPUs. And I'm showing a bunch of charts here where we are comparing MI300 to an equivalent NVIDIA device. And it's comparing across different types of models, language models, image generation models, multi-modal models, things like that. And the key message here is that in some cases we are performing better, in some cases we are equivalent. And if you look at the bar here, which shows the Llama 70B, I talked about memory advantage that we have with MI300. You cannot fit the model in a single node on NVIDIA, but you actually can fit the model and kind of get good performance on single node. So that's one of the benefits of having more memory in a single device. So before pre-training, once you scale out, you want to make sure that you get good performance on these single nodes. And what we do at AMD is, as some of these models come out, as DeepSeek came out, as the next Llama 4 comes out, we work hand in hand with some of these companies. So on the day these models are launched, you also get good performance on AMD devices. So next, when we talk about scaling, scaling to thousands of GPUs, this needs a lot of parallel computing. You're essentially trying to compute the same thing on multiple devices. And there are several ways of doing parallelism. There's data parallelism, tensor parallelism, a few different kinds. The simplest of them is data parallelism, where you're trying to fit your model on single GPU, and then you use different sets of data on each GPU. In training, you do a forward pass, and you try to accumulate the results back from all the GPUs, and then you update the weights and restart that process again. So when you do this, essentially, there is a time of window where all your GPUs are sitting and waiting for data to come back. And these moments where the GPU is sitting idle is called pipeline bubbles. And when you're trying to scale, when we say linear scaling, you go from 1 GPU to 8 GPU to maybe 100 GPUs, you expect to have 100x performance of 1 GPU. But these bubbles sort of kind of come in the way of getting that linear performance. As you start scaling out, if you don't address them well, you'll start losing performance. So there are other techniques where, for example, FSDP is fully sharded data parallelism, where you can actually shard your model across GPUs and also the data, where you can hide some of the communication behind compute. So as some of the GPUs are waiting for data, they're working on the next layer, so you can hide these different things. And each of these parallelism strategies have their own unique pros and cons. And what we do is we take these models and then we try to scale it up to maybe 32 or 64 GPUs and show how you can get linear scaling. And the plot there, what you see is basically a horizontal line, meaning you get the same performance per GPU as you start increasing the number of GPUs. And that's the goal. And we have examples of various models which we showcase performance on AMD GPUs to have linear scaling. Once you have it on 64 GPUs, you can just replicate it to well over thousands of GPUs. And we worked with customers with kind of giant, large 1,000+ GPUs where you get this linear scaling. So that's a little bit about pre-training. Once you have these models that are pre-trained, the next task for us is to fine-tune these models. Essentially, not everyone is trying to pre-train, right? A few handful of companies like Meta and some of the giant companies have the resources to pre-train. But once you have these pre-trained language models, you can start targeting these models to the use cases that you're interested in. So here I'm showing an example of a full weight fine-tuning, meaning you're updating every weight in the model using AG News dataset, which is a dataset that comprises of a bunch of news articles, and it tries to categorize them, what data, what type of news that is. And the thing I wanted to highlight here is if you look at the distribution on the top right, see that some of the input sequences have really small sequence length, some have very long sequence length. And when you're trying to train, you want to fit the maximum sequence length. So you're basically padding zeros where you don't have enough data. So that actually reduces the efficiency a lot in your training. So to overcome that, there are libraries like Torstune, which allow for you to pack these data sequences to better use them, or they also allow for variable sequence lengths. And on AMD, we do support some of these. And the bottom, I'm showing a couple of graphs where we again compared with H100, show slightly better performance. And also we trained it to convergence, and you can see with tens of millions of tokens, we are able to converge a little faster than H100. The other popular way of doing fine-tuning is called LoRa. I don't know how many of you are familiar with LoRa, but LoRa is a way of creating small adapters which adapt your model to certain use cases. So instead of training all the weights, you see the image in the center up there, instead of training all the weights, what it does is it decomposes your matrix into two lower dimensional matrices. And then you only train that part of your model when you're trying to fine tune. The advantage is because it's a lower dimensional space, you don't need as much data to fine tune your model. So you can use smaller amounts of data. And when you're trying to inference, you kind of take these weights and add it back to the original weight matrix, and you have the exact same number of weights. So your inferencing does not change, but you have different adapters that can be targeted for different use cases. And this is very popular to adapt pre-trained models to your specific use cases. And again, here I wanted to show a little bit of example of how we compare against NVIDIA for these use cases. On the bottom right, I'm showing an example where on a Llama 70 billion model, so in the previous slide, I talked about LoRa. One of the key aspects there is the rank of your lower dimensional matrix. The larger the rank, the more you can adapt to your models. So at the bottom, I'm showing an example where for a particular rank of 8, you can fit some amount of data, a particular batch size on H100 and MI300, and you can get better performance than H100. But because we have a memory advantage, you can start increasing your batch size further and keep improving the performance. Similarly, on the right, I'm showing a couple of examples where you have a rank of 8 LoRa that can fit on H100. But because you have additional memory, you can think about increasing your rank. Like you can make it rank of 16 or further and continue training on single MI300 node. Or on the other end, you can also start increasing your sequence length. So essentially, MI300s have more memory, and with that, it comes with a lot of flexibility. You can either pick longer sequence lengths, or you can increase your LoRa rank. So it essentially is equally capable on compute, but it has additional advantages that you can take benefit of at MI300. So next, we'll switch to post-training, and I'll hand it off to Mehdi to talk about post-training.
Thank you so much, and hi, everyone. I'm going to continue on post-training, and I'll also introduce one of our most recent projects we did on this direction. So post-training is a smart way to evolve model, and it's a lightweight training approach for adapting pre-trained models to new tasks, to new domains, and new architectures. So post-training basically is designed to reuse the information we gain through pre-training, and we have an efficient approach to go towards new tasks, and actually the goal is to also keep the performance of the base model that we are working on. So if we compare pre-training and post-training side by side, we can see in terms of training data, for post-training, actually we use just billions of tokens versus pre-training in which we have trillions of tokens. In terms of training time, for post-training, we're talking about hours of training, but for pre-training, we usually deal with days of or even months of training. And in terms of computation and GPUs, pre-training needs a lot more like GPUs than post-training, actually. Now I want to go from post-training to the concept of hybrid models, and also we see the connection between the two. So you might be familiar with transformer models, like they are dominant in AI, dominant model architecture in AI now. Transformers suffer from quadratic complexity, especially imposed by self-attention. And also they require like a lot of memory for KV caching mechanism, especially for longer sequences. And we want to, let's say if we want to deal with these computational issues of transformers, like one approach is to replace token mixing happening in, let's say, attention mechanism with other alternatives like Mamba, which is a state space model, works in a similar way than similar way to RNNs. And we have also other architectures like MLA, multi-head latent attention, proposed by DeepSeek, and it's a solution to compress KV cache using a low-rank decomposition approach. So we might be able to replace attention in our architecture with these Mamba or MLA blocks. But the thing is that if we replace all the attention blocks, then the performance or accuracy of our model would drop. And that's why we think about the concept of hybrid models, in which we replace not every attention block in the original model, but some with, let's say, Mamba or other alternative efficient architectures. But then the question would be, if we change the architecture, let's say from attention to hybrid models, then we have to pre-train the model from scratch. And what we want to do is to avoid such a huge cost or expense of pre-training. We want to see if it's possible to, let's say, adapt or move from pure attention-based model to a hybrid model, and we just do adaptation to a lightweight post-training. The answer to this question is actually we can do post-training, and we have done such a practice in AMD. We call our model Zebra Llama, a family of actually post-trained hybrid models. And one important feature of this model is we train it through post-training, and also it's very efficient or extremely efficient compared to transformer models. It's composed of Mamba and MLA blocks. And in order to actually reuse the knowledge, the pre-training knowledge of the transformer, we have our particular weight initialization approach. So based on the correspondence we have between the attention-based models and Mamba-based models and MLA-based models, we use actually the attention weights to initialize Mamba weights, and also for MLA we have SVD, singular value decomposition approach, to initialize our MLA weights. In the second stage, aside from initialization, we have another refining solution to basically improve the approximation of weight initialization we had in step 1. So we go to another intermediate layer distillation to match the output of intermediate layers between our pure MLA, pure Mamba, and like the base attention model we have. And then at the end, we want to compose a hybrid model. The question would be, how are we going to select which layers should be Mamba and which layers should be MLA? Our solution is based on actually smart layer selection. And this smart layer selection comes with a sensitivity analysis for all layers of our efficient models, pure Mamba and pure MLA. I don't go to the details of that, like you can follow in the paper. But based on that sensitivity analysis, we decide which layers of the hybrid model should be MLA and which layers should be Mamba. We trained different model sizes, 1B, 3B, and 8B. These models are able to compress KV cache significantly. We don't use much, let's say, training tokens. In terms of performance, we are able to match the performance of these hybrid models with the original base model. And you can see the training time is just a few hours on a single node, MI300 node. In terms of throughput, you can see the basically the plot. The red basically dashed lines are Zebra Llama models, 8B models, that in terms of throughput with respect to different generation lengths, we can have a consistent throughput compared with like even other hybrid models like Mamba in Llama. The other aspect that we also evaluated was the trade-off between accuracy of the model versus KV cache size. And you can see here we compare our model with other state-of-the-art models in the literature. The green ones, the green Zebra Llama models, in terms of KV cache size, are pretty competitive. And they use very small KV cache compared to, let's say, pre-trained models or even other hybrid models. But in terms of LM harness eval score, like they are very competitive to even, let's say, pre-trained Llama 3 model, which is trained on trillions of tokens. So for the sake of time, I just move to the next part, which is like our last part of our presentation. Yeah.
I'll just take another couple of minutes to talk a little bit about how to get started on AMD. First thing is, I want to say it's pretty easy to get started on AMD. There's a lot of material out there. We regularly publish blogs on how to get training and inferencing going on AMDs. We also release bi-weekly Dockers for training and weekly Dockers for inferencing. What this does is it basically makes sure that the latest models get really good performance on AMD devices. These Dockers support language model generation, image models, video generation, multi-modal models. So we keep expanding the scope of these Dockers. And it also supports different libraries, PyTorch, JAX, MaxText, Megatron LM, Hugging Face Accelerate. So there's quite a few that are popular, but we support all of the ones. And in addition, on the right side, I'm showing a bunch of open source models that AMD has pre-trained from scratch. And it's open source. We open source the recipe. We open source the model weights as well. The goal is, obviously, you can pick these models, fine-tune, and use it, but also it showcases how to train on AMD, what you can do to get the best performance out of AMD. And each of these comes with pretty detailed blogs on how we got these performance. And if you're looking for a very basic starting of how to get containers working, how to get training working on ROCm, how to get the multi-node training going, we have a lot of blogs for each of these. And the Dockers on MaxText, PyTorch, Megatron, each of these, we have QR codes. Each links to a blog where you can get these details. And finally, I'll leave with this. With the launch of MI355 last Thursday, we also launched AMD Developer Cloud. What this is developers like yourself can log in there, create a login, get access to an MI300 GPU at an hourly rate. And I think there's also a very brief period where there are some free credits that you can get. But do go to this link, register and see if you want to give it a try. There's MI300s and MI325s available for you guys to give it a shot. I think, with that, we'll close the talk, and happy to answer any questions.
Thank you so much for the talk. I'm Razi. I'm curious to know, maybe this is a very naive question, because usually I use one GPU, not that much. But if you are using a lot of GPU, is there any chance that we can use better AI or more up-to-date AI tools so that we can use less GPU? Just curious.
It depends on your size of the model. Like in the first part, I talked a little bit about the MI300 GPU, right? Each one has about 129 gigabytes of RAM. So if your model, either for inferencing or training, is up to 70 billion, it should fit in one GPU. When it starts becoming even larger, like if you're thinking about 405B or one of those larger models, you have to go to multi-GPU. But on the other end, if you're actually trying to do even smaller models, there's virtual GPUs. You can take one GPU and split it into 8 GPUs. And if your model is really tiny, you can actually use one of those virtual GPUs. So it can span the spectrum of, sub-GPU to multiple GPU, depending on the use cases.
Thank you for the talk. The question that I have is about basically the Zebra Llama model, right? So there were some talks about quantization. And I guess what you can say about quantization of these hybrid model?
We didn't try that, to be honest. So let's say based on what comes to my mind, we should be able to quantize, let's say, hybrid models like Mamba-based models similar to other language models with, I guess, similar challenges on the way. But we have not tried that yet. Can be an interesting direction, actually, too.
I think our goal was to maintain accuracy and with the same number of weights and show how quickly you can post-train a model. Any additional optimizations that do on a standard foundational model, you can quantization, any post-training quantization techniques or QAT, you can continue applying and get benefits on these models as well.
I guess actually I don't remember if these PTQ approaches, like for example GPTQ, right? They were okay for Mamba-based models. But I guess actually, if you remember, if they were kind of applicable to this Mamba, and then do you expect some of these models some of these quantization approaches that is already there, right? Can we just easily apply them on top of Mamba Zimba?
Zebra Llama, I think it should be. I really don't see like particular barrier for that, to be honest. At least not something that comes to my mind right now. Yeah, it should be doable. Yeah.
So with CUDA, there is an increasing trend that people are fusing kernels, like Triton is there, and Liger kernel, everybody uses that. And there's a lot of optimization that we benefit from for training. So is this something that AMD is investing on and looking into, or are you waiting for open source community to come in and do the same?
It's a combination of both. We do support Triton. Triton developers from OpenAI work closely with AMD. So Triton has supported this fused torch compile, for example, with PyTorch is also supported where you can fuse kernels. In addition, for some very low-level kernels, we do have basic fused operations that we will release as part of our open source kernel library as well. And they'll have some examples as well. So it's a combination. We do target some, like the ones that are really benefit from understanding the hardware. AMD comes in and fuses those kernels and releases those. And then there are some examples like Triton, which you can benefit from. So Torch Compile, actually, if you're using CUDA or NVIDIA, you should be able to port over directly to AMD GPUs as well.
Great, thank you.